And our story in fact began about 14 billion years ago when the universe was born. But we started learning about the story only about 100 years ago when it was discovered that our universe is expanding. In particular, what was found by Hubble is that the far away objects are moving away from us, and further away the objects are, the more is their speed. So this description of the universe has come to be known as the Big Bang theory, and this was confirmed by the discovery of cosmic microwave background radiation, or in short what is called CMBR, in the 1960s. So what this radiation represents is a uniform thermal radiation at 2.733 degrees Kelvin, which is quite low by today's standard. But just the existence of this radiation tells us that it must have been much hotter in the past, because as the universe expands, the radiation cools, so you can extrapolate backwards and conclude that there is a hot gas of radiation in the past, and that's one of the signatures of Big Bang theory, of the expansion of the universe. So by the middle of 1990s, most scientists working in this field thought that we have a very good understanding of the Big Bang theory. And according to the story that was then understood, the universe was thought to contain three kinds of sources of energy or mass density. The first kind is ordinary matter, which is made of ordinary stars, interstellar dust, Earth, us, etc. Then there is a mysterious source which was called dark matter. We still don't know what the dark matter is. It's an unknown source, but it behaves as ordinary matter as far as gravity is concerned. So for the purpose of today's talk, we don't need to distinguish dark matter from ordinary matter. And then there is of course the cosmic microwave background radiation, which has a very small effect at present, but it was important in the past because the radiation was hotter and denser. So the story, the picture that we had at that time was that the universe started with a bang, and that's why it started expanding. But because gravity is an attractive force, as the universe expands, the various objects start pulling each other towards each other, pulling each other, and so the expansion of the universe would have been slowing down. Okay, that was the understanding in the middle 1990s, and everyone thought that we understand what the universe looks like. This changed in 1998 by two independent experiments, and what they discovered was that the expansion is actually accelerating instead of slowing down. Unlike the usual intuition, which tells us that the gravity is attractive and hence the expansion of the universe must be slowing down, what they found is that the expansion rate today is faster than the expansion rate in the past. So by now we have a reasonably good explanation of what the universe looks like. We have a reasonably good understanding of what the universe looks like. And according to the best explanation that is available today, 73% of the energy density in our universe exists in some unusual form, which has come to be known as the dark energy. Sometimes more technical word for this is cosmological constant. So this dark energy is a strange new kind of matter which has negative pressure, and this causes gravity to act as a repulsive force. And that's the reason why the universe is accelerating. The remaining 27% is mostly made of ordinary matter and dark matter, which I had already introduced earlier. And an insignificant fraction today is in the microwave background radiation. So that's the current picture of the universe that we have, and it works reasonably well. Okay, even though we don't understand fully what the various components, what is the origin of these various components, what gives rise to dark energy. Okay, I'll have a little more to say about this later, and what corresponds to dark matter, that we still don't understand. But at least if we assume that this is the content of the universe, you have a good understanding of the expansion of the universe. So dark energy has now become a household word. Many people, most people probably have heard of it in some form or the other, okay, at least in the scientific community. But what is perhaps not widely appreciated is how the discovery of dark energy has changed our perspective on the future of the universe, how the universe will evolve in the future. So today's talk will be the story of the future of the universe, and this is also the story of our future, hopefully, provided of course we survive pandemics, nuclear war, climate change, and whatever other exciting events may come. So let me begin by what I'll call the classical story. Okay, the story of the future of the universe according to the classical laws of motion. Now I have already told you that presence of dark energy causes the universe to undergo an accelerated expansion. And this in fact is a consequence of Einstein's general theory of relativity, which is the theory of gravity that Einstein had developed again more than 100 years ago. Furthermore, as a consequence of the same Einstein's equations, one can show that dark energy density remains constant as the universe expands, unlike ordinary matter, which gets diluted. We are familiar with the fact that if you have a certain amount of matter in a given volume, and if the volume expands, then the density will fall. Dark energy doesn't follow this rule. Okay, dark energy density remains constant as the universe is expanding. So this means in particular that the acceleration will continue in the future. This expansion of the accelerated expansion of the universe that we see will continue in the future. And one can also predict, based on our current understanding of the content of the universe, that the size of the universe will double in about every 12 billion years. So because of this accelerated expansion, it is physically impossible for us to reach very far away places in the universe. Because the far away places are moving away so fast, okay, at such an accelerated pace, that even light signal cannot reach those places. So this is what I have said here. Even if we travel at the speed of light, we can reach objects which are at most at a distance of 18 billion light years from us. Anything that is beyond 18 billion light years is simply not accessible, and this we can show by following the standard classical laws of physics. So a technical word for this is that these objects, which are farther than 18 billion light years from us, are outside our horizon. This horizon, in some sense, is the limit of how far we can reach if we try hard enough. Furthermore, as the universe expands, more and more objects will go out of our horizon. So it's as if the universe is getting split into multiple universes which have no communication with each other. It's not that there is a sharp wall separating these different regions, but it's simply that it's impossible to reach one region from another. So this idea of multiple universes sounds like a science fiction, but it's in fact a reality. And to convince yourself that this is a reality, let me just note that at present, the part of the universe that we can see has a radius of about 46 billion light years. In particular, the cosmic microwave background radiation that we are seeing today is coming from a distance of that kind, 46 billion light. So you certainly know that that part of the universe exists. Okay, at least it existed in the past. And this is about 2.5 times the size of the present horizon. So which means there are parts of the universe that we can see which are already out of our horizon. Okay. Those parts we can see, but we can never reach. So 2.5, this is 2.5 times in length. So in volume, it's about 15 times. So this means that the observed universe has already split into more than 15 parts that cannot communicate with each other. And we expect that the actual size of the universe is much bigger. Okay, not just what we can observe, there must be something like beyond. And so it contains large number of parts that cannot communicate. So this slide may be a little technical, okay, and it's not really necessary for understanding the rest of the talk. Nevertheless, it gives a very useful insight into what I have described so far. Okay, so let me try to explain what this diagram represents. So between these two horizontal lines, the part of the diagram between these two horizontal lines is a picture of the entire history of the universe. So in this diagram, along the vertical axis, I have plotted some function of time, which I am calling capital T. This is a known function which you can calculate. And at late time, it has the exponential dependence. So one of the special features of this way of parameterizing time is that the entire history, which in fact lasts for infinitely long, it started at some time, but then the universe will hopefully live forever, at least according to classical physics. That entire history has been made compactified into a finite, right? Just by choosing the coordinate system, this variable. So this is the beginning of the universe. That's where the Big Bang took place. This is where we are today, and this is the end of the universe. Right? This is actually small t. The physical time is infinite here, but capital T ends. So here I have said the capital T is some function of time, and the physical distance, what you see in the horizontal axis, is the distance measured from us. But this is not quite the distance, it's distance scaled by some function of time. So equal distance here and here, okay, or equal length here and here doesn't mean they're the same distance. Okay, you have to multiply by this function. So the special feature of this coordinate system is that light always travels at 45-degree angle with the coordinate. And since every object travels slower than light, every massive object travels slower than light, that means in a given time, the reach of any massive object should be less than what the light can reach. So massive objects travel at less than 45-degree angle with the coordinate. Right? Like for us, we are traveling along this line. Okay? Stationary object. But we can send out spaceships which can explore the region between these two 45-degree angles from ground. Now, from this diagram, we can see that if we send out light signal, then even if you wait for infinite time, right, which corresponds to this upper horizontal line here, we can only reach a certain distance here, not beyond. So this is the size of our horizon today. We also see that if we wait for a little longer, or maybe a lot longer, then by the time we have reached this point in time, the part of the universe that we will be accessing is much less, right? From here, we can access only this part. So what we have within our horizon today, right? Let's imagine that we are here and another galaxy is here, right? We are just evolving along vertical direction. Then today we may be able to access some of these galaxies by sending out spaceship. But if we try to reach those galaxies from here, we will never be able to reach. That's the sense in which I said that the universe splits into many parts which cannot communicate with each other. We can communicate with the other parts, but not yet. Now, it looks from here as if the size of the horizon is itself shrinking, but that's somewhat misleading. Because remember, I told you that equal length in this diagram doesn't mean equal length in terms of physical distance. In fact, one can show, after we take into account the scaling, that the physical size of the horizon more or less remains the same. So at any given point, any given instant of time, we can send out light signal to reach objects that are within 18 billion light years at that time. But there are many objects which are within 18 billion light years today, which would have gone much beyond 18 billion light years in the future, and hence they are inaccessible. They become inaccessible. Now let me come back to the future of the universe again, okay, in non-technical terms. So we see that expansion of the universe pulls objects apart, but it doesn't pull everything apart. Okay? For example, the objects inside our galaxy will not be pulled apart by the expansion of the universe. And that's because the objects within our galaxy are what are called gravitationally bound systems. They have their own gravitational attraction towards each other. And that is sufficient to hold them together against the expansion of the universe. So it's not that because of the expansion of the universe, the solar system will be torn apart. Okay? The solar system will remain bound together, and in fact, our whole Milky Way will remain bound as a single galaxy. In fact, our nearest large galaxy is Andromeda. There was a possibility that that will be torn apart from us by the expansion of the universe, but it turns out that the Andromeda is in fact approaching us. There is the Andromeda is not, galaxies are not completely stationary. There is a relative velocity between Andromeda and us, so the Andromeda is actually approaching us, and we expect from numerical simulation that eventually it will merge with the Milky Way and become just one single galaxy. But most other galaxies outside our local group of galaxies will eventually go out of our horizon. And if we try hard enough, today we may be able to establish civilizations. Today they are very much within our reach. So we can send out spaceships and we can establish civilization in those parts of the galaxies. But eventually we'll lose touch with them forever. So once they go out of our horizon, we can never access. So in the far future, our local group of galaxies will be the only ones that will be within our horizon. And when the last star of the galaxy dies, life as we know today will not be possible. Because at least the life, what we think of life today is supported by star dying. And this is expected to happen over a period of 100 or 1,000 billion. And indeed, this will be a somewhat sad and lonely end to our civilization. That will be isolated, we will not be able to communicate with other galaxies. And eventually, when the last star dies, our civilization will die. Now, we'll see that in the quantum world, which I'll be describing now, life will be a bit sadder perhaps, but it will be much more exciting and adventurous. So this, let me turn to what quantum mechanics has to say about the future of our universe. So the story of quantum mechanics begins with that of a particle sliding on a hill. Okay? So let's imagine that you have a hill with two valleys, okay, which are called A and B. And imagine that you have a particle, okay, which just slides in this hill. And from our basic knowledge of quantum of physics, classical physics, okay, or just basic common sense, we can say that the particle can be at rest either at this minimum or at this minimum. Okay, everywhere else it will start flying down. So let's imagine that it's at rest at A. Then everyday experience tells us that it will continue to rest at A forever unless we disturb. Okay, of course, it's possible that we just push it and then it goes above the 1. Okay, but as long as you don't disturb it, it will continue to rest at A. Right? This is what classical physics tells us, and this is what also common sense tells us. But according to quantum mechanics, there is a tiny probability that the particle may suddenly disappear from A and appear on the other side of the hill from where it can slide down to B. This probability is very, very small, at least for the kind of hills that you are familiar with. But nevertheless, it's a small but non-zero probability. Now, our interest, of course, is not on a particle on a hill, but on the whole universe. The dynamics of the universe is described by what is technically known as quantum field theory. So, for the purpose of today's talk, we can think of quantum field theory, or we can think of field theory. A field is like having a particle at every point in space which moves in some hidden direction. Okay, so imagine that instead of one particle sliding on hill, we have a particle sitting at every point in space, and it has some hidden directions into the particle moves. Okay, that's not the direction in the normal space, but some hidden directions. So let me give an example which is perhaps familiar to most of you. Magnetic field, right? Magnetic field, is described by three components: the x component, y component, and z component. And every point P in space, the x, y, and z component of the magnetic field takes certain value. The Earth's magnetic field, for example, at this point, it can be measured, and you can measure it x, y, and z component. And you can draw an analogy by saying that it's like having a particle at every point in space, and the particle has three coordinates, which are bx, by, and bz, but these are not the physical coordinates of the particle. These are as if their coordinates are on some hidden directions. Okay? Let's just put that. So the simplest possible field, and that's all we will need for today's lecture, is called a scalar field. Unlike magnetic field, which has three components, a scalar field has only one component, and we'll call this component H. So it is like a particle at every point in space which moves in one hidden direction instead of three hidden directions. And just like the motion of a particle on a hill is controlled by the potential energy, right, which is the height of the point on the hill. Similarly, the motion of the particle is controlled by a potential, which is I'll call P. It's a function of the field H. So for a given configuration of this field, right, which means the given position, given value of H at every point in space, there is an expression for the energy of the system, energy of the universe. Okay, and the energy of the universe takes this form. Okay, so it has this form. There is a potential, okay, which we have to integrate over the whole space, okay, because it's like a particle at every point in space. But there is also a gradient term, which tells us that if you have, say, two neighboring points in space, then having H different in the neighboring points costs some energy. Imagine that you want H to have certain value here and a different value in the neighboring point. Of course, you can have it. Okay, that's a possible configuration, but it costs energy to have such configurations. Okay, and that energy cost is what is written in this first term, gradient of H. Again, the technical details should not be very important for us, but I have just written down the explicit expression to guide our isolating. So let's now suppose that the form of B is what we had seen earlier, okay, like a hill with two values. So this V represents potential energy per unit form. And a scalar field with such a potential can be at rest at either of the two minima. We can either have the scalar field taking value at this point, okay, which is at point A, everywhere in space, or you can have the scalar field taking value at the point B, everywhere in space. And these two possible states of the system are called two phases of this thing. And here the word phase I am using in the same sense as ice and water being two phases of H2. So here we have a scalar field with some particular potential. The scalar field can be either in this phase or in that phase, and these two phases correspond to these two particular configurations of scalar fields correspond to these two phases. Now it turns out that the properties of the theory in these two phases are typically very different. Even the properties of elementary particles like the mass and charge of the electron will be different in different places. If in the phase A the electron has certain charge and mass, in the phase B the electron may have a different charge, or the electron may not even exist. There will be different kinds of particles in phase B. In particular, dark energy density is the value of the potential at the local minimum. So, for example, if the universe is in this phase, then we can say that this phase has positive dark energy. And if the universe is in this phase, then we will say that the universe has negative dark energy. So, in quantum field theory, there is a natural source of what dark energy stands for, and that is simply the value of the potential energy density in the particular phase that describes us. Now, let's consider the effect of quantum mechanics. So, for this, let's again recall the story of particle on a hill. We have said that if the particle is sitting at A, then classical law tells us that it can suddenly tunnel to B. Because it can just appear on the other side of the hill and then it just rolls down. That's quantum mechanics. Sorry, I didn't say. Classical mechanics tells us it will sit here, but quantum mechanics tells us that it can tunnel and reach B. So, given this, we can ask, is it possible that a similar tunneling can happen in a quantum field? Now, imagine that we have these two phases of a scalar field theory, and suppose that we are in this phase. Suppose the universe that we are living in corresponds to phase A, right? The scalar field is here. Is it possible that it will tunnel from here to B, A to B? Now, it turns out that the probability that the scalar field will become from A to B everywhere in space at one time, at the same time, is zero, because you have to make this transition everywhere in space, which means that if the probability of transition in some small region is something less than 1, then you have to raise it to infinite power, and any number less than 1, right, which is raised to infinite power, is always zero. So you cannot simply make a transition from A to B everywhere in space at the same time. However, something else can happen, and that is this: that it can happen that if you are in phase A, which means that the scalar field has the value corresponding to A everywhere in space, then in some small region of the universe, the scalar field can become B, can it tunnel to B. So, if suppose the quantum mechanics produces a bubble of B of this kind, then we can ask what will be the subsequent fate of this bubble. What will it do if quantum mechanics produces a bubble of this size? So, once a bubble of this size is produced, this bubble will try to lower its potential energy. We know that everything tries to lower its potential, right? If we drop a ball, it falls because it tries to lower its gravitational potential. So, once this bubble is produced, it will try to lower its potential energy. But there are two competing effects. One is that it can lower its potential energy by expanding, because B has lower potential energy than A. But recall that there is also a gradient energy. So, on this wall, because it makes a transition from B to A, the field has to change from the value at B to value at A. So, there is a gradient, and that gradient energy is proportional to the surface area, because over the whole surface area, the field is changing from B to A. And that surface area, it tries to shrink the bubble, because surface area, the energy associated with the surface area can be lowered by reducing the area of the surface. So there are two competing effects. The potential tries to expand the bubble, and the surface energy tries to shrink the bubble. But if a sufficiently large bubble is produced, then one can check that the volume always wins. because volume always grows as cube of the radius. The surface area grows as square of the radius. Okay, so the volume energy wins, and then the bubble starts expanding. So quantum mechanics has to do the job of producing a sufficiently large bubble, and then classical effect takes over. Okay, just minimization of potential energy, and the bubble starts expanding. So the bubble begins expanding, and in that process lowers its potential energy. But of course, the potential energy has to go somewhere, and it goes into the kinetic energy of the wall. So as the bubble expands, the surface accelerates. It begins an accelerated expansion. This is different from the accelerated expansion of the here. That was purely a classical effect. Here, the bubble is being produced by quantum effect, and then the wall is expanding. But the net result is that soon the speed of expansion of the surface approaches the speed of light because it's continuously accelerating. And eventually, it will convert A to B everywhere. So for this reason, A is known as the false vacuum or a metastable vacuum. It's called a false vacuum because as long as you are sitting in A, you have no inkling that you are actually in an unstable situation. But once quantum mechanics produces a bubble of this kind, it just gets destroyed. Okay, the bubble will just simply expand and destroy A, and it will not remain the vacuum. So given this, we can ask what will be the state of any living or non-living object in A during this process. Imagine that A is ours. Okay, we have stars and life and galaxies and so on, right? What will happen to those if a bubble of B expands into our universe? And the answer is simply instantaneous destruction. It will be instantaneous destruction because even the elementary constituents like the electrons, which would make up objects in A, do not exist in B. Right? Even if they exist, they have different masses, different charge. Right? So there will be no atoms or molecules that we are familiar in the new universe. So everything that we know in A will be instantaneously destroyed. Eventually, maybe they'll make some objects in B, but they'll look nothing like what we are familiar. So for this reason, from the point of view of A, it's apt to call this the killer bubble. So now we turn to the central question, okay, that should interest us, and that is, are we living in a false vacuum? Can we meet this kind of fate in the future? Now, this possibility is not new. This possibility has been known for more than 50 years, that we could be living in false vacuum. But there are some relatively recent developments which have generated renewed interest in this subject. And this has to do with the experiment at CERN in 2012, which discovered the first example of a scalar field or elementary scalar field in nature, and that's called the Higgs field. We are familiar with the discovery of Higgs particle, but that has associated with it the Higgs field, which is a scalar field. And it has exactly potentials of the kind that we saw. It is governed by some potential. So you can ask, are we living in the false vacuum of the Higgs? Now, when you construct the theory of Higgs field, or when Higgs constructed the theory of Higgs fields, he wrote down a potential which is nice, okay, which has a nice minimum at H equal to B. You can easily see it's positive definite, right? So this has a minimum at H equal to B and minus B. And according to the theory that describes as the standard model of the elementary particles, H equal to B is the vacuum where we live, and it is certainly a minimum. So the original theory was designed to make sure that we are not living in a false vacuum, we are living in a true vacuum. But quantum mechanics spoils the game again, where it turns out that even though we write down some classical potential, okay, where we make sure that we are actually living in a true vacuum, so we are not in danger, There are other kinds of quantum effects, other than those that I talked about, the bubble production, which corrects the potential and which produces other minima. And once the potential is corrected and once other minima are produced, then we can again ask, are we at the true minimum of the corrected? Now, these quantum corrections depend on the mass of the top quark and other parameters of the theory. And it turns out that the situation is so finely tuned that we, based on the current measurement, we really cannot say whether the other minimum, we certainly know that there is another minimum, but we cannot say for sure whether the other minimum is above ours or below ours. So there is every possibility that we are actually living in a false vacuum. But even if this is true, the probability that we will be tunneling to that other vacuum currently, okay, from our current observation is extremely low. So you don't really have to worry about the Higgs field causing transition into the false vacuum. But the actual situation is in fact much more complicated, because there are theoretical reasons to believe that there may be many more scalar fields in our theory. We have discovered only the Higgs, but there is reason to believe that as we probe deeper and deeper, at higher and higher energies, we will find more scalar fields. And among these unknown fields, there may be scalars whose false vacuum describes. We have no way of knowing. So again, we come back to the central question: are we living in a false vacuum? The only way we can know this for sure is from some fundamental truth, where the list of fields and the potential is fixed from some fundamental principle. If we have such a theory, then we don't rely on experiments. So you can simply try to base our understanding on that theory and see if the vacuum that we are living in, whether it's false or true, okay, whether you are at the absolute minimum or whether you are in some local minimum for the potential. Now, string theory, okay, that's the subject that I work on, is an attempt to have such a fundamental theory. It's a proposal for a theory that describes all the elementary particles and their forces. And according to our current understanding, string theory has many scalar fields with complicated potential, with many local minima and maxima. So this has come to be known as a landscape of phases in string. Okay, if you think of every local minimum as a phase, the string theory has a plethora of phases. This is an oversimplified version of what string theory tells us, because here I have, of course, drawn only one scalar field. But even for one scalar field, you can see that you can have a very complicated potential with many ups and downs. Some of them have positive dark energy, some of them have zero dark energy, some have negative dark energy, as you can see. Where dark energy is the height of the potential from zero. So if string theory is the right theory, then one of these minima will describe the phase of the theory that you are living in. The current situation in string theory is that we have found three phases whose elementary particles have properties similar to the ones we see in nature. Unfortunately, we do not know of a phase yet that describes exactly the elementary particles we see, which has the correct mass of the electron, mass and charge of the electron, correct mass and charge of the muon, and correct mass and charge and of all other elementary particles that we see in nature. This can be summarized by saying that even if string theory is the right theory, at present we do not know our position in the landscape. Nevertheless, you are not totally in the dark. And that's because we know of dark energy. So discovery of dark energy tells us that in the phase that we are living in, the potential is positive, because you have positive dark energy. From theoretical studies in string theory, we know that string theory has many phases with zero or negative potential. Okay, I said that we don't know our position in the landscape, but we certainly know many phases in string theory and their position in the landscape. And there are many phases with zero potential or negative. So if string theory is right, then we must be living in a false line, because we are at a local minimum which has positive potential, and you know that string theory has other local minimum which are negative or zero potential. So assuming then that we are living in a false vacuum, the next question will be, how likely is it that we shall be hit by a killer bubble during the next one? What is our half? So to answer this, we need to know our location in the landscape. Right? If we knew our location on the landscape, we could calculate the probability of transition into these various other vacuums, and we can figure out how likely is it to make that transition. But this is not possible today because we don't know the position in the landscape. So if theory cannot answer the question, can we invoke experiment? Can the current experimental understanding of the universe tell us anything about how likely we are to be hit by a killer bubble in the next one? And for that, the only experimental result that is relevant is that our universe is about 14 billion years old. And this tells us that unless you have been extremely lucky, the risk of a hit per year should be less than 1 in 10. So otherwise, you would have perished by it. So the very fact that you have survived for 14 billion years means that the probability that we will be hit by a killer bubble cannot be much larger than 1 in 10 to the 10. And that's all we can say. Now, let me also say that 1 in 10 to the 10 doesn't mean that you have 10 to the 10 years to live. Right? Because probability is somewhat strange concept, right? I mean, there are many radioactive atoms, right, whose lifetime, whose half-life is much larger than 10 to the 10. Okay, but we see them decay. Right? Even though our universe is less than 10 to the 10, it is about 10 to the 10. And this is probability. So if the probability of being hit in 1 year is less than 1 in 10 to the 10, we can be hit by tomorrow or for the end of this talk. The probability is somewhat low, but it's there. So you can ask, how small is this number? 1 in 10 to the 10. And here is a way to estimate, to get some idea of how small is 1 in 10 to the 10. Now let's suppose that one day a small asteroid hits the Earth and destroys everything within 100-meter radius of it. Then the probability that you will be within that region is about 1 in 10. So that's the estimate of how small this number is, small or large. Now it is small, of course, but some people would worry, right? If they know that tomorrow an asteroid will hit and it will destroy everything within 100 meters, there are some people who worry that you may be within that 100 meters. Okay, so it's not unimaginably small. So I promised you some excitement, and I hope that you would agree with that the possibility, however small, that tomorrow you may be wiped out by a killer bubble, and the rest of the universe will follow suit, is at least more exciting than waiting for a slow death over billions. Okay, so now the last part of the talk. Okay, I promised you two things. One is excitement, the other one is adventure. So we now turn to the adventure. And it turns out that, as in most adventures, we need to leave home. So let's recall some of the basic facts we have learned. We have learned that at present we can access a certain region of the universe that is given by a horizon size. We also learned that with time the expansion of the universe will convert into a multiverse with many universes. And the rate of increase of the number of distinct universes is controlled by the expansion rate of the universe. Okay, every 12 billion years, our universe will double in size, which means in volume, it will grow 8 times. Okay? It will create 8 separate universes within our universe, within our horizon. We also learned that killer bubbles will make some of these universes unlimited. But even killer bubbles have to follow the laws of nature. They cannot travel beyond the horizon, right? Because they expand at the speed of light, and even light cannot cross the horizon. So the rate of decrease of the number of livable universes is controlled by the rate of formation of the killer bubble. So you have two competing effects. Okay, one is the production of new universes, the other one is the destruction of existing. And if the rate of universe production exceeds the rate of destruction, then the number of livable universes will increase it, even though some of the universes will be destroyed. The question is, how does this help us? And it doesn't help us if you are lazy. But if you are not lazy, so we can make use of this. Let me explain how we can make use of this. So as I said, if we remain confined within our own galaxy, then our annihilation probability will be controlled by the rate of destruction. Now, of course, it is possible that the rate may be so small that by the time the killer bubble reaches us, our galaxy would have burnt its fuel anyway and we would have perished. In that case, we do not care, right, if the killer bubble hits us. But it will be a pity if we perish when the galaxy still has a lot more time, right, which is, as I said, 10 to the 13 to the 10 to the 14 years. But we can overcome this fate if we spread out into the currently accessible universe, right, which is one horizon. Over time, this region will split into many universes. And then even if some of these universes are destroyed by killer bubble, the others will survive. So while one single civilization cannot survive, their destruction will be controlled by the destruction rate. Collectively, civilization may continue to live on. And one can in fact do a quick calculation that shows that spreading into n universes increases the collective life expectancy by a factor which is given here. Because even spreading into 2 universes increases the life expectancy by 50%. So you may be thinking now that, okay, we have to do this heroic act of spreading into the other universes. But let me just remind you that the real hero of the story is dark energy. But it is dark energy that is pulling the universe apart. And all we can do is to ride the expansion that is driven by the dark energy. So this brings me to the conclusion of the talk. And I'm sure that by the time you leave the hall, you would have forgotten most of what I have said. So I've tried to summarize the conclusion in one single sentence, which you may remember for a little longer. And that's here. Dark energy helps those who help themselves. So in your spare time, think of ways to populate the universe with your horizon. Thank you.
Thank you so very much. I don't know. I mean, I'm sure Elon Musk has listened to him. So, though he has not ventured outside the galaxy, but I don't think the time is. I mean, we're not that far away from that next adventure. Okay, so Professor Sen has agreed for a question answer session. If you are, hold on, another Elon Musk in the audience. Okay, so we have 2 mics. So we have 5 to 10 minutes to go before we close the question and answer session. Please feel free and shoot your questions.
Sir, could you please go back to slide number 11, the conformal space-time diagram? So, what does the x coordinate signify, like the horizontal coordinate?
Yeah. So the horizontal coordinate. And one idea is that our universe that we are living in itself is a killer bubble inside some other universe. That we are inside a bubble, and that's the current understanding of how our all that.
Was that just, I mean, that would have been another Big Bang before the current Big Bang, which
Yes, at least one. But those part, I mean, that early hits it will not be able to keep. That's not really something early hits. That is awesome.
basically we don't have the evidence of.
We don't know from current experiments what. But theoretically, it's certainly possible. Right, like that our universe itself began by at some kind of expansion of the bubble inside some other.
Okay, so that means, I mean, after the death of the last star, there can also be another Big Bang for the new creation.
Yes, indeed. So I mean, if you make transition into this Big Bang, right, that can have its own start. And
Thank you.
it's that dark energy density, right? So A has certain density, I think. That's a very good question. So indeed, not in classical mechanics or the reference for the potential has no effect. But in gravity, it does have it. Because gravity couples to energy. So when you bring gravity, then the zero of the potential energy actually acts. And you cannot just shift it by arbitrary. Well, you can think about the physical entity because that's where the field changes from one one to another. So that defines what the one, where the field is changing. And that is what is
So yes. So initially you said that in a given universe, killer bubble is created. So will there be any interaction between the killer bubble and the universe?
there should be. Except that because the bubble one is expanding at the speed of light, that interaction cannot be made by something else. So if, for example, a killer bubble is expanding, coming to our casting, there is no way you will know the existence of a killer bubble. Where its fall is traveling at the speed of light. And any signal will also come to our killer. So it's impossible for us to know that a killer bubble.
Okay, like, but before that, we can send a signal somewhat into the other universe in that.
We can, yes. But will not ever get it.
Like through the killer bubble, there is some possibility of two non-interacting universes interacting with each other.
Yes,
Not exactly interacting, but at least the signals.
yeah, we can send signal inside other but by signing light. That one.
Okay.
That is our
Thank you. Next one. You said that if the bubble is big enough, it can have the energy to throw. What is the
that's usually very tiny and microscope. That depends on the details of the potential. But typically it's very, very fine.
Right? We can go what we need to go to a higher potential and it will like maybe first it will get destroyed because of the energy situation. This microscopy don't affect anything. But if it is big enough, it have been a killer bubble also, right?
But it will always try to bring down.
Yes, but it could be a killer bubble at the
Yeah,
initial
for a little while and then it will come down. But because the microscope, it will not really affect it.
So this time. So inside the killer bubble, the physics would be different. Uh, do you expect? Do we expect the fundamental constants to change? Like the Planck's constant, the value would be different, or
The fundamental constants are we still said the units. The Planck's constant and then the speed of light. And in string theory, it's the what for the fundamental length of the string. Those will remain the same. But everything else will. And everything else they derive from concept. So mass of elementary particle.
Sir, for a time, if we assume that we are living in a false bubble and false vacuum, and in the coming times, some killer bubble engulf us. So what will happen to the black hole which exists in between our universe present?
Well, the black hole will remain. Black hole will remain a black hole because that's gravity. But it will be inside the other.
And rest of the stars and other stuff will be completely destroyed.
All matter will come.
Sir, does cosmological constant also describe the formation of killer bubble?
Well, see, in this, no, the cosmological constant is the height of the bubble. What we call the cosmological constant is really the height of the bubble.
So, is there a relationship between killer bubble and wormhole? Are they sort of similar?
So, wormholes are defined actually. Wormholes are actually purely classical object. Classical.
there was one hole of the wormhole inside of a universe and the other hole was out of our horizon. So will there be any way of actually communicating with the part that has gone outside, like from another wormhole?
At least not. I would say that these things. We said that one doesn't understand the quantum mechanics, quantum gravity very well. The normal wormholes are not visible. There is the idea that sometimes the quantum effects in gravity can give rise to wormhole like yeah, that can be complicated. But I would say that this story is not completely understood. And after taking the quantum effects of gravity, so that can be at least not with the present understanding.
So I have two questions actually. So one is if we have a bubble that is centered around us, which is our observable universe, which is 18 billion observers, and there's one more such right after our edge, one more such bubble right outside us, which will not be able to communicate with. So, but if there is some other observer who's at the edge of our universe, they will be able to communicate within another 18. So
Yes.
they will see both of them. So if we have a bubble that forms to that observer there, so that will keep expanding. It will never reach us, but won't its effect be visible within our universe at that edge point, like within our universe?
But from that edge point, you not receive the signal. So, okay, let me give the very extreme example. And I told you that our universe today has this 15 area. The visible universe, what we can see, has split into 15 separate parts. Some of those multiverses may already have been explored by people. And we will never only know that they existed at the time when the light started to come. Whether they exist today, we don't know. There will be no way of communicating.
Okay, this clarifies that question. And one more is if a bubble forms inside us, the light that we shine into it will go into it, right? So if our own universe is within such a bubble, won't there be a remnant signature of the previous bubble it belonged to? The previous universe it belonged.
Yeah, if we are living at close to the edge of the bubble, we will be able to see something. But the boundary is very far, and we already know that within our horizon, there is no such thing. So, indeed, if you are near the edge, we will be able to see the picture. But right now, we are very far from it. It's true that very boundary.
So what is the universe expanding into?
What is the universe expanding into? Well, the universe is actually not expanding into anything. It's just that if you follow the equation, you find that the distance between the edit point is becoming large. It's like imagine the surface of a balloon and the balloon expands. Normally, you think of the balloon as expanding into 3 dimensions, but you can forget about the third dimension and just think of the surface of the area of the balloon. And it just expands, every point gets order. So the expansion of the universe is like it's not expanding into anything. Just every area of point are getting order.
Like in case of balloon, if we believe that it keeps on expanding, for it not getting burst, there should be space expansion. So
Yeah,
how is
the point, okay, it's hard to visualize, I understand, but to think of it, that imagine that you have our 3 dimensions, and you can imagine the distance, the 8 points will increase as far as this. That's the big. Or you can say, okay, you can also think of it this way. Imagine the points are fixed, but the actual physical measurement that is made, and that measures something that is not the coordinate distance, but coordinate distance multiplied by some function of time. And the function of time is actually this.
Okay, so it's like we stick some forms in the balloon, and the balloon keeps on expanding. He said
Yeah.
this.
Instead of thinking of the balloon keeps on expanding, you can think of the scale that you use to measure the distance keeps on shrinking. Then in that scale, the distance from the point will look large. these two are entirely equivalent of describing cells. If you are uncomfortable with the idea of something expanding, you just think of the scale that we use, whether that is the points are fixed at separate, the points are fixed, but the scale gives them to the apparent distance.
Sir, and one clarification. As you mentioned, the whole universe changing from a false vacuum to the lower minima would be infinite, as there would be infinitely many points within the universe. So integrating over the whole universe gives us zero. So for any even in case of any finite volume, that encases itself like infinitely many points for the field, right? So even in that case also there are infinitely many points. Won't that also again give us zero, or is there any quantization that leads us to having particular finite volume for finite like part of it?
So that's again a very good question, and it's part of the way I describe it qualitatively, it's not quite the right way. But to think of it this way, so if you really think of this as infinitely many points, then it even the difference in potential and it is finite, would have been there are infinitely many points, each point, each particle that had its, you would have expected that the difference between the actual potential energy of the first 8 seconds will be. But that's not infinite because we actually have integral. Because the sum over infinite number of points, then it will be infinite. But the way you define an integral, you have to define it as a limit, multiply by some whole constant of time, and then take a limit. And the same way you calculate the problem, and you find a finite. After the volume is finite, you get a finite.
Yeah. So I had a question about the surface tension and the shrinking of the bubble. So let's say, like a false vacuum has decayed and a bubble is charging expanding. So inside the bubble is the most stable state, and outside is the less stable state. So yeah, if the bubble starts small enough, then maybe at the boundary there's not enough activation energy enough for the bubble to expand. But what will cause the bubble to shrink? Won't the bubble just stay constant at a kind of equilibrium?
So typically what happens is that either at the exactly at the junction, it may be at the equilibrium, but at a very small, I would say a laser thing, right? At some very particular value of the radius, the things will vanish. But that's very unstable. Anything smaller than that, the bubble will shrink. Anything larger than the bubble.
I don't understand the function of the surface tension, like how the surface tension is coming. What is causing
the extension is coming because of this stuff. The gradient of H square. So whenever H changes, it costs energy, right? So at the surface of the bubble, H is changing from here I have got it as not wall, but actually there is a smooth transition from V to N, so there is a difference. That's where the constant is.
Take the last question now.
So you have spoke about a plethora of landscape that string theory provides us, and there are many minimums of the curve. And you have also said that potential of dark energy is positive, so we can exclude the scenarios where dark energy is negative. But then you also said that we haven't yet found any universes which replicate or have the nature of fundamental particles that we have. So in spite of all these hurdles that string theory is facing now, and it has been 40 years almost since Michio Kaku conceived this in 1980s or something. So it has been 40 years now, and why are we still chasing this theory? And I'm asking you, has this theory, is this theory becoming obsolete now after 40 years of evolution?
Yeah, let me. The point is that right now, what we have some experimental facts which improve that we understand that standard the particle physics very well, reasonably well. We also know that we have a solar fact. And we know that gravity, the part of gravity that we know, classical gravity is enough to experiment. We also know that quantum theory describes the total gravity. Now, suppose you want to understand a theory, a theory that describes the whole thing, and it will describe a solution, but it will describe anything. One can show that it is not possible to combine classical data with quantum science, quantum probability. It's an inconsistent. There are some questions you can ask for which this cannot provide it. You have to find a theory which incorporates everything that you expect. And that has to be a theory that implies that are both gravity, quantum mechanics, and particle. Now, at this stage, you can take two. One is that okay, you don't have experimental evidence, so you don't give up and accept that. The other viewpoint is that you have some experimental data and you try your best to explain that. And here, what string theory does is that we don't understand the theory. It tries to find a mathematically consistent description. These are the potential of incorporating. And that's what string theory does. We're not liking the person of the here about understanding what are fundamental theories. But if you want to understand what fundamental theories, you have to either work on string theory or find something else which does it. And that's all I can say. String theory, you are still working on string theory because you feel that it's important to understand how the person based on what data. Have more data, of course, it's good. I can incorporate. Don't have, then you have to whatever data you have and try to understand how.
So
so much worried about history, you can find out that when Higgs particle field was predicted, and find out how much time it took for us to experiment and discover. So the timeline scale is not that important. If I remember correctly, it also took 30 years or more than 30 years. And similarly, we all believe that particle physics standard model is correct. We pushed ourselves to understand everything experimentally. But remember that theoretically, whether it's Higgs particle, whether it's W boson, Z boson, everything was predicted much earlier than experimentally really discovered. Okay? Suppose I was working that time and I was working and find that some theory is giving a new particle called Z boson, which is not known, and I can throw down my calculation and throw into the dustbin. You know what would happen to my, I would have lost the Nobel Prize, right? So we are still interested to get Nobel Prize, etc. So don't not get nervous about 40 years.
I'm the timekeeper, so I close the question and answer session. I'm sorry, I have this dirty job timekeeping aspect. Professor Sen, thank you so very much for your presence of listening to this young minds and answering them. Please. Guys, please don't move out. I just have an announcement to make. I just changed the day span and the high tea will be served inside. So please don't go on. If Andromeda is expected to merge with Milky Way in 15 billion years time, 10 billion years time, there's no reason why we should be glad about this theory will not be years. So hang on and have patience. Will not be alive to serve in any case. And the probability of we are hitting by a balloon tomorrow is just 1 upon 10 by 10 to the power 10. So anyways, the eternal optimist in me is very even more optimistic. So before I move on to the second session of guys, please don't move out. This is very selfish of you to move on. And I've told outside that don't serve anyone with. So before we move to the second session, may I invite Professor Sudhakar Pandey to please join Professor Sen in the dais. Not listening to anyone now. Okay, so going ahead, moving on with the tradition of honoring or felicitating our academic toppers, the past recently concluded academic session. See, remember the graduating batch, the graduated batch left the campus with their degrees, but all other years students also need to be facilitated, and the tradition that we have, we do it on this day. So I just hope the award winners are here. So I would again request send to please the winners. We will be distributing certificates today. There is a cash award attached with it. The cash is going to be class of some cash. So for the odd semester of 2021-22, let me start the proceeding. The batch topper is for the first semester is Priti Priya Das Behera with an SGP of 9.64. Please give a round of huge applause. Should not actually stop. Priti Priya Das Behera with an SGP of 9.64. The third semester, it's Priyanshu Parida with an SGP of 9.55. For the fifth semester, batch 2019, it's Husna AB with a perfect 10. For the seventh semester, it's Nitha Naham P. Nitha Nahan. Again with an SGP of 10. Now moving on to the subject toppers for each school. For third semester, School of Physical Sciences, it's Sagar Prakash Barad with an SGP of 9.45. Sagar Prasad Barad doesn't seem to be here. Then for the School of Chemical Sciences, it's Priyanshu Parida. Priyanshu again. For the School of Mathematical Sciences, it's Arjav Jugani with an SGP of 9.17. For the School of Biological Sciences, the four-ways tie. Advita Sharma, Ayush Panda, Farhin Khadar, and Shashwat Saurav Sahu with an identical SGP of 8.80. There could be a mix-up with the certificates. No, all of them get more, but yeah. Advita, Ayush, Farhin, and Shashwat. This is it. For the fifth semester, for the School of Physical Sciences, it's Aditya Prakash with an SGP of 9.83. For the School of Chemical Sciences, 5th semester, it's Husna AV with an SGP of 10. For the School of Mathematical Sciences, it's Prashnodeep Sadhu Khan with an SGP of 8.83. Prashnodeep Sadhu Khan. I don't think he's around. He knows that money is getting transferred to the account. For the School of Biological Sciences, it's Manali Banerjee with an SGPA of 9.67. For the 7th semester, School of Physical Sciences, it's Fida Salim with an SGP of 9.83. The School of Chemical Sciences, it's Nitha Nahan, Apratim and Ashish. Can you guys come to the front row, please? Apratim Chaudhary, Ashish Mishra, Aditya Pal. So this is for the School of Chemical Sciences, Nitha Nahan. For the School of Mathematical Sciences, it's Apratim Chaudhary with an SGP of 9.67. Even semester award winners, please come to the front row if you know that you are getting prizes. For the School of Biological Sciences, it's Ashish Kumar Mishra with a CGP with an SGP of 9.33. And the overall topper in terms of CGPA for the first semester 2021-22 academic session is Aditya Pal with a CGPA of 9.67. Bag rakh le. So the next set of awards, let me announce the names. Please come to the front rows. Priti Priya Das Behra, Sajak Kumar, Rudhi Ranjan Sahu, Ashish Kumar Mishra, Jyoti Prakash Malik. Please come to the front row. Advaita Sharma, Prayag Ranjan Sahu, Arab, Arjab Jogani, Sajak Kumar, Shweta Sasindran, Rudhi Ranjan Sahu, Ayanava Mandal, Rita Dev Bharti, Sarbajit Majumdar, Ashish Kumar Mishra, Jyoti Prakash Malik, Apratim Chaudhary, S. Gautameshwar. So I start with the next set of awards for the semester toppers for even semester of 2021 and 22 academic session. For the second year, with an SGP of 9.73, it's Priti Priya Das Behra. For the fourth semester, it's Sajak Kumar. Sajak Kumar. Okay, moving on. For the sixth semester, it's Rudhi Ranjan Sahu with an SGP of 10. For the 8th semester, it's a two-way tie. Ashish Kumar Mishra and Jyoti Prakash Malik with an identical SGPA of 9.83. Moving on to the subject toppers for each school. For the 4th semester, School of Biological Sciences, it's Advita Sharma. Advita Sharma with an SGPA of 8.50. To the School of Chemical Sciences, it's Prayag Ranjan Sahu with an SGPA of 9.45. For the School of Mathematical Sciences, it's Arjav Jogani with an SGPA of 8.70. For the School of Physical Sciences, it's Sajja Kumar with an SGPA of 9.64. I assume it's not wrong. For the 6th semester, School of Biological Sciences, it's Swetha Sasindran with an SGPA of 9.33. For the School of Chemical Sciences, it's Rudhi Ranjan Sahu with an SGPA of 10. For the School of Mathematical Sciences, it's Ayanabha Mandal with an SGPA of 9.83. For the School of Physical Sciences, it's a two-way tie again. Ritadev Bharti and Sarabjit Majumdar with an identical SGPA of 9.67. Ritadev Bharti and Sarabjit Majumdar. Moving on to the 8th semester for the School of Biological Sciences, it's Ashish Kumar Mishra with an SGPA of 9.83. For the School of Chemical Sciences, it's Jyoti Prakash Malik with an SGPA of 9.83. For the School of Mathematical Sciences, it's Apratim Chaudhary with an SGPA of 9.50. For the School of Physical Sciences, it's S. Gautameshwar with an SGPA of 9.67. And for the overall performance, that is CGPA for the semester, goes to Preeti Priya Das Behra with an CGPA of 9.68. Moving on to the, we have 4 more hours. To the MSc portion of the integrated MSc PhD program. For the odd semester, it was Abhik Shah with an SGPA of 9.80. And Ritvika Majumdar with with an SGPA of 9.32. So Avik received just 2 awards for the first semester and also for the event semester. So the first semester SGPA was 9.80, and second one. Ritvika also receives both the odd semester and event semester awards. For the odd semester, her SGPA was 9.32, and for the event semester, it was 9.41. Yeah, with this, we conclude this felicitation program. And I know you guys have left if I had announced earlier. I was actually lying. No high tea is being served inside. Thank you so very much. And with this, we actually conclude the session for the Foundation Day lecture and subsequent felicitation of. Hey guys, stay back, stay back. I didn't ask you to leave the hall. I said I was lying that the packet will not be served inside. We still have programs. Okay, so before we move on to the last segment, let me request our director, Professor Sudhakar Panda, to honor the guest of the day, Professor Ashoke, with a small memento of appreciation from our side. Hang on, I have not asked them to hand over packet to you. Please don't go out. Thank you so very much, Professor Panda. And with this, we actually conclude the Foundation Day lecture. And I don't think we would be. I mean, we can thank Professor Sen enough for being kind enough to consent for this delivery of this Foundation Day. And yeah, thank you so very much for making our day. Guys, please move outside. And I know there will be a long queue for the food. ज्ञान के लिए भूखे तो है ही. Please honor the queue